And if we manage to do the dihedral groups today, we can have a tutorial session tomorrow instead of the lecture, when you will understand everything.
That is optimistic. Are you sure?
Yes.
I've lost my pen. Oh, that's not funny. Oh, no.
Do you have any questions? Why is it pointing into my?
That is a question. One of the homework questions. Oh, but it doesn't have to be until next Monday. Oh, why have I been doing it then? No wonder I didn't understand it.
Of course
We
not.
did say that to you. No, you didn't. We did.
Okay, dihedral groups. So a bit, that's an important example of groups. Killian likes them. Have you met a dihedral group before? Oh yeah? What was it?
Were you looking at triangles?
Yes. But why triangles? You can do any polygons, regular polygons. So Dn is the oh, that should be blue. The nth dihedral group is the group of symmetries of that. Of the regular n. For example, D6, that's the hexagon. Yeah. So what can you do with the hexagon? You can rotate it. Okay, so when I just look at the vertices and I rotate it, what's this called? Anti-clockwise.
Yes.
Something wrong? I can write it as a permutation of the vertices, which is 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes to 1. So it's like a cycle. Okay, what else can you do with it?
Reflect it.
Yes, you can reflect it about an axis. Pick an axis. Okay, so what does it do? 2 goes to 6?
Yeah.
3 goes to 5? And 1 goes to 1, and 4 goes to 4? Okay, what else can you do?
middle of the edge. I can't say it. Instead of reflecting between 2 points, between the middle of 2 opposite edges.
Change where the axis is.
Yeah. Yeah.
Like that.
Yeah. Yeah.
Is that what you meant?
That's what I meant.
Good. Just, I understand her encoding of encryption. Okay. Yeah. So you can do this. As well. So this is what is this? It's 1 6, 2 5, and 3 4. This is SR. Do you believe me? So first, so we write it right to left. So 1 goes to 2, goes to 6. Yes. 6 goes to 1, goes to 1. Yes. 2 goes to 3, goes to 5. Yes. 5 goes to 6, goes to 2. Yeah. Working. 3 goes to 4, stays 4. 4 goes to 5, goes to 3. Yeah, that one. What else can you do? Oops. So you can do many things. You can turn it. So all the rotations, it's just not this one, but you can rotate by, well, this one was 60 degrees. You can do 120 degrees. So that's just r squared. And that's going to be 1, 3, 5, 2, 4, 6, I believe. So this is anti-clockwise 120 degrees. And there are others. How many are there in total? By not by listing them, but by counting them. What is the order of D6? So how many different rigid motions like that? 12. Why is it 12?
Because the order's always 2 and 4. Because there's 6 rotations, including the identity, and there's 2 reflections. 3 through vertices and 3 through the middle of axes.
Yes, but how would you know that's everything?
I'm joking.
Okay.
If anything else would just be a repetition of these talks. One of those, yeah.
Well, it would be, but how do you know?
Because it's just there.
It's that easy to.
It's just common sense. It's just there.
Okay. So an argument that persuades me is the following. Look at 1. You can put 1 wherever you want. Okay, so there are 6 possibilities for vertex 1 to map. And then 2 has to be next to 1. So it has to be one of the neighbors. So wherever you map 1, for example here, 2 has to be one of these 2 neighbors. Okay? So that's two possibilities for vertex 2. And then everything else is determined, because if you put 2 here, then you have to go 3, 4, 5, 6. And if you put 2 here, you have to go 3, 4, 5, 6. So mapping 1 to one of these, any of the 6 vertices, and mapping 2 to one of the 2 neighbors completely determines the whole mapping. Okay? So that's why it's 12 for me.
Yeah. I was going to say,
Okay, so because 6 possible images for the vertex 1, and then 2 possible images for vertex 2 to be a neighbor. And then the rest is determined. Okay, so now this generalizes, so one can say that it's an observation. Observation is a type of theorem which you just observe because the proof is easy.
that's mine.
So the order of the end dihedral group is to n, because the book says. But same argument goes through. You have n possible vertices as images for vertex 1. And then 2 has to be a neighbor. So again, there's only 2 neighbors. And the rest is determined. Well, you have to go. Okay. What's the order of R?
Well, yeah, resolution.
Yes.
6.
Yes. So in fact, you might have observed already when we were doing permutation groups that if you have a cycle of length k, its order is k. So for transpositions, the order was 2 and so on. And so for S, the order is 2 because you reflect and you reflect again. You're back where you started. Okay.
Oh, okay. Sorry.
So what are the elements? So D6. I want to list them all. So I have the rotation. I said I have an R to the 6, and that's the identity. And then I had SR, and I can have SR squared, and I can have SR cubed, and I can have SR to the 4th, and I can have SR to the 5th, and I can have S, which is S times R to the 6th. And this is all the 12 elements of the group. Oh no, there's no comma here. And that's all of them. Okay? That's because I'm telling you. But you have to think about it. So this is an observation. An observation is an easy theorem which doesn't need a proof almost, because everybody can observe proof. So Dn is generated by R and S. Can we define what it means?
What? Define what?
To be generated by something. Well, we said to be what it is to be generated by one element. I'm not entirely sure whether we actually said what it means to be generated by two elements. So what this means? If you're taking R's and S's and their inverses and timesing them, all you ever get is Dn and the whole of Dn. Okay. So in this case, you can't. So yeah, you can. But so with one element, it's just one element squared, cubed to the fourth, and so on. All the positive powers, all the negative powers. But here you have to allow kind of a mixing. Yeah, so you do R to some power, S to some power, R to some power, S to some power. So Dn is all the R to some power, K1, S to some power, K2, R to some power, K3, K3, for all finite sequences of integers, K1, K2, Kn. Okay. So you prescribe your, what are they called? Exponents. They can be negative because then you're taking powers of the inverse. They can be positive. They can be 0 as well. Then you're just skipping it. So we've already seen two different groups, really. They are called V6. In fact, D6 was number 1. It was the symmetries of the n-gon. Of the hexagon. Okay, I'll do the n of the n-gon. So what is the symmetry of the n-gon?
Is that a one?
Yeah, that's the one. Bit of a misprinted one.
Is it a 1 in the bracket or is it just?
Yes, it's like number 1.
Right, okay.
It's going to be a number 2. So the first one, so when you're talking, what is the n-gon? What does it consist of? It depends, but normally people would think that the n-gon is everything in the n-gon, not just the vertices, right? But also everything in the middle. Yeah. So in fact, if you have a rotation of the n-gon, not only it tells you where the vertices go, but also for any point inside, it has to be mapped somewhere, not just the vertices. Right? So symmetries of the n-gon the mapping should really be that the domain should be all the points, all the vertices, also all the points on the edges, also all the points in the interior, and they all get mapped somewhere. And then without the word of warning, I just wrote the vertices, right? So that was the second point of view. So it was a permutation group. On 6 letters, was it? We called it?
That's what we-
Yeah, okay, so let's go.
Is it not M? It'll be an N lines.
Oh. I apologize. It's N. Now there's a third point of view.
It's 202.
I actually don't really do that.
Now a new one. It's the N is the group generated by 2 elements R and S that satisfy the following. So when you do the rotation n times, you get the identity. When you do the reflection twice, you get the identity. And there has to be something that tells you how they interact. Because like this, you could be rotating away and you wouldn't get back. But you also say that if you do a reflection, a rotation, and a reflection again, what do you get? Huh? How would you know?
What was it?
Okay, so I have the hexagon. Reflection gives me a hexagon. It will always give me a hexagon. Rotate. Okay, so 1 moved there, 2, 3, 4, 5, 6. Reflects. Reflect. Done it. 2, 5, 3, 1, 4, 6. So that's like rotating it backwards. Okay, so you can so this is another point of view in group theory. You can start writing letters S and the powers. So some S's, some R's, S's, R's, R's, S's. But whenever you see like SRS, you can replace it with R minus 1, R inverse. Whenever you see n R's in a row, you replace it with the identity. And you can do replacements like that. And so some sequences of R's and S's are going to give you the same elements. And that's a group. Okay. It's a very weird thing. Yes. This is how maths works once you get past the like primary school maths, like differential equations and formulas.
What happens if you don't pass them?
Oh, you're working on it. That's a good sign. So it's theorem 5.3. It's this, in fact.
That's not a theorem. That is a theorem. It's a space, he's not pronounced that it's a theorem. He's just put it in a box. I just said it. Oh, I didn't see that. Didn't see that smaller box.
Okay, so yeah. Now you have different ideas of what one group can be. And it's usually quite important in maths, so well, important. Yeah, important. It's a good idea to always keep in mind that there are several different points of view that you can have of the same object. Especially in algebra, because algebra is like kind of codifying abstractions. So here we have some abstract object, which is just a group. And it's really quite hard to get a handle on that abstract group without picturing what it could do. But at least now we have two kind of concrete things that it can do. It can be some transformations of n-gons, including the interior points. You can also see it as just permutations of a finite set, so just the vertices of it. And then you can see it as a group which is very abstractly defined. Well, we're taking all sequences of R's and S's, and in order to work out whether the two sequences of R's and S's are the same, we're only using those three equalities given there. Does it make any sense?
Screen selection.
Yeah. I don't mind doing that. Better?
Yeah.
Have we done the proof of this? Well, not working. Theorem 523.
I put it in the. Ow.
Yeah, it's in the book. So the proof, if you wanted to prove that Dn is the group, then you'll say R is a rotation, S is a reflection, and these equations are already satisfied because if you do the rotation n times, you get back where you were. And I'm not writing it because you wouldn't see it because the camera doesn't work. But it's all written in the book. And is there anything else that you want to know about dihedral groups? What? Okay, so this is probably as much as we need to know about the dihedral groups for now. Like there is this kind of I have a note that I made last year about free groups. So a free group, free one, yeah, free like as a bird. Not like you don't have to pay. Okay. So a free group is just like that one. So you can take, so you say what your generators are. For example, you could say my generators are R and S. And then you just write sequences of R's and S's and their inverses. And all elements are like that. And there are no equations. So if you write two sequences and they're different, like you write RRS, R squared S, is different to RS, and they're never the same. So unless you really write, now of course, R and R inverse cancel out, but that's the only thing. So you don't have any cancellations, and that's called a free group. And the dihedral group is not a free group. It's called what's called a finitely presented group. So is it working? No. So don't read it. Yeah. Yes, because it's very useful.
I'm quite worried then.
It's not in the book though.
I know, exactly.
Can you post it on me?
Yeah. No, you don't. I mean, you need to know about it just like informally for your information. It won't be tested. But it's quite so. So there is a like you can. I'll talk about it again when we're doing normal subgroups and stuff. Because, yeah, yes.
You know how you said that the proof of theorem 5.2 is in the book?
Is it not?
At the bottom it says, we will leave the proof that SRS equals R inverse as an exercise.
Well, yeah, but we've just seen it.
Oh, yeah.
No, but that was just...
That was just for 6, yeah. We've seen it for 6.
Yeah, so we got proof. Just okay.
No, but...
Just go through it yourself.
So what else? What does it say? So yeah, so SRSR. What is SRSR?
SRS.
Yes. Why?
Because
Because
a rotation on reflection.
Reflect, rotate, reflect, rotate, and puts it back. So when you can see that, you can prove that SRS is R inverse. It's the same thing. You just keep it for later. Okay. Then there's in the book, and I'm not. What's happened? Even the camera's not working. Something's gone very wrong.
Oh, we're not recording this.
It's definitely on earlier.
It was.
Well, we've not. Well, are you still recording? Yeah, it's recording the noise. I'll stop it.